Welcome to all my avid learners. We will be taking a look at a dynamics, or more specifically a kinematics problem in this video. I've chosen to consider problem 12-90 found on page 48 of Hibbeler's 13th edition textbook titled Engineering Mechanics Dynamics, copyrighted in 2013. Here before us is a drawing of the problem we're considering, and as you can see, you have a boy who is attempting to kick a soccer ball over a 3-meter tall wall that's located 6 meters away from him. And so the question we're trying to figure out is, at what smallest speed, v0 or v0, I might refer to it, and corresponding angle theta 0 and or theta 0, should he kick the ball in order to clear the fence? If you've been following my videos for any length of time, you know that wherever appropriate, I like to make a small side note that's pertinent to the context of the science problem we're looking at. And so perhaps the most important minimal or extremum type of problem we could ever ask, or question we could ever ask, is that of what is the minimal thing a person must do in order to have life? And I'm not talking about the short life that we have in this life, that is to say, a person might live for a few years, a few decades, whatever, and then they die. I'm talking about what comes after death, meaning on the other side of this short existence, we're going to have an eternal existence, and there are only one of two possibilities. Either a person is going to inherit eternal life, or they're going to be utterly separated in a place called hell and be eternally damned. And so the question is, what is the minimal thing a person must have in order to inherit that eternal life? And the answer is found in the first letter of John, chapter 5, verse 12, where we find very simply that he who has the Son, that is to say Jesus Christ, has life. He who does not have the Son of God does not have life. And so the answer is very, very simple. You may ask, well, what must a person do in order to have the Son, in order to have eternal life? And the answer is very simple. Very simple. Actually, you and I can really do nothing. It was what Jesus did on the cross on our behalf. So he took our punishment of sin by dying on the cross, and he makes that as a free gift available to anyone, that free gift of pardon, available to anyone who would receive it. If you're interested in knowing a little bit more about this, I've produced a short 12-minute video titled One Question that you can check out, and I go into great detail about that. Before I leave this subject, let me just point two additional things related to this. One is that there is, for those of us who have accepted the Son of God and accepted Jesus Christ into our hearts, there is something known as the Bema Seat, or the judgment seat of Christ. And this is going to happen where all of the believers are going to be judged, not to determine eternal life, because that's already been settled, but to determine rewards. So you might think of this as people going through a graduation ceremony. Maybe all of those people are graduates, and yet only a few select graduates will actually get rewards. Like you might say, this person is graduating summa cum laude, or something of that nature. But there is also a second type of a judgment, and this is known as the judgment of nations, or another terminology used is the judgment of the separation between the sheep and the goats. And this is where, in fact, those people who have not received the free gift of pardon made available by Christ, they will be eternally separated from God in a place called hell. And that's going to be a very grim type of judgment. So, my friends, those of you who have not received the free gift of pardon made available by Christ, again, I urge you to check out the One Question video. Okay, now let's go back and check out this problem that we're trying to figure out here. The very first thing I like to do in these sorts of problems is to put down a coordinate system, and as you can see, I've already drawn in a coordinate system. The horizontal direction I'll call x, and the vertical one I'll call y, and as you can see, it is centered right over where the ball is originally, so the ball is at the origin of my coordinate system. And that's kind of arbitrary. You can put your coordinate system anywhere. However, there are better places to place it and less favorable places to place it, and I think this is the most favorable of all choices. The next thing that I would do is, and this is something you've studied if you've looked into vectors, is to break this vector v naught into its horizontal and vertical components, and we can do that very simply by saying that the horizontal component, which I will call v sub 0 x or v naught x, is equal to the magnitude of the hypotenuse on this right triangle, which is the v naught, times the cosine of the angle theta naught. Okay? And once you have that, you get the other one for free. The other one, which is the vertical component, is going to be the v naught y is equal to the v naught times the sine of theta naught. Okay, now let's go ahead and write our kinematic equations. And we will do these along the horizontal and vertical directions as well. And let's start with the horizontal one. So if I write the horizontal one, I'm going to get x is equal to x naught plus v naught x times the time t plus a half of ax times t squared. And we will note right away a few things here related to this equation. If you look at the ball along its trajectory, let's take some point along its trajectory, let's say that one. The only acceleration that's acting on this ball is straight downward, and that is due to gravity. So it's just the gravitational constant of acceleration g, little g, which in this system of SI units or metric units, we have meters, so we know that we're dealing with metric units here. G is going to have a value of 9.81 meters per second, or 9.81 meters per second squared. And notice that it's going downward, and we said that upward is positive, so it's going to actually be negative. However, the point that I wanted to make out here with related to the x value of the kinematic equation is that there's no x directional acceleration. So this ax is gone, which is great news to us because we can get rid of a pretty unpleasant looking term at the very end of our equation. Another term that we can get rid of is this first one after the equality. Our initial position horizontally is 0 by virtue of where we placed our coordinate system, and that's why I said, you know, picking your coordinate system is arbitrary, but there are better places to pick it than others, and so that drops out right away. And then one other thing that we know is where the ball will be as it's clearing the fence. From a horizontal standpoint, it's going to be 6 meters away. That was given to us in the problem itself. And so now we are in a position where we can back solve for the time. All right, so t is equal to x over v0 x. And let's plug in what we know. We know that x is 6, and that v0 x we already solved for. That is v0 times the cos of theta 0. And so now we have an expression of time with these two unknown pieces, namely the initial velocity or speed and the initial angle theta 0. Okay. Now let's go ahead and write our second equation in the vertical direction, and it's going to be identically analogous to the one above, except instead of x's we put y's, and so we have y equals y naught plus v0y times the time plus a half of a sub y times the time squared. Okay, and as we just said a moment ago, this ay is really equal to minus 9.81 meters per second squared. Okay, and the v0 is once again 0 by virtue of our coordinate system, and this y value is equal to 3 meters. That's how tall, that's how high the ball has to be in order to clear that 3 meter tall wall. All right, so let's go ahead and write this out, and we're going to get 3. Let me write the 3 out to the left a little more. So we get 3 is equal to v0y we found is v0 sine of theta 0, and that is multiplied by the time that we solved in the step above for the x direction position, and that's 6 over v0 cos of theta 0, and plus a half times minus 9.81 times the time squared, that is to say 6 over v0 cos of theta 0 being squared. Okay, we note a couple things real quick here too. We note first of all that the v0s in this first term after the equality on top and bottom cancel. Okay, we also note that sine over cos is by definition tangent. So I could write in my next line, I could write this as 3 equals 6 times the tangent of theta 0, and then for this other term, this last term, if you multiply a half times minus 9.81 times 6 being squared, if you multiply all of that, you find that this is equal to minus 176.58 over, and then the bottom there is being squared, so you get v0 squared times cos squared theta naught. And then what I would recommend to do is a little massaging algebraically on what we have here so that we can actually solve for this. And so what we will do is, let's go ahead and multiply both sides of this by the denominator way out on the end there, v0 squared cos squared theta naught. And if you do that, you get 3v0 squared cos squared theta naught is equal to 6 times, you get, let me write the tangent as sine of theta naught over cos of theta naught momentarily, times, of course, the v0 squared cos theta naught. I'm going to write cos squared theta as cos theta naught times cos theta naught. And then you get the just the constant surviving term at the end, minus 176.58. And so now look at this. You get a cos of theta naught on the bottom canceling with one of these on top. And so in the next step, I'm going to do a little more algebra and say, let's go ahead and divide both sides by 3. Right? So look at this. You get v0 squared cos squared theta naught is equal to, I'm going to bring this v naught squared out in the front. So let's write this as v naught squared times 6 divided by 3 is 2 times the sine of theta naught times the cos of theta naught minus 176.58 divided by 3, and that is equal to 58.86. And so look at what we have in this next line. We get, let me do this. Let me move this term over to the left, and I'm going to move this term over to the right. And before I do that, I'm also going to point something out that we've talked about in previous videos. This 2 times sine theta naught cos theta naught is actually equal to sine of a double angle. Okay, so I hope you recognize that by the addition formula. Sine of a plus b is sine of a cos b plus sine of b cos a. And so if you just do sine of theta naught plus theta naught, that which is sine of 2 theta naught, you'll find that it's in fact exactly 2 times sine of theta naught cos of theta naught. And so all right, now let's move terms around and keep on going with the algebra. So we're going to find that we get minus 58.86 on the left is equal to, I'm going to factor out a common v0 squared times sine of the double angle minus cos squared of the single angle. And now let's go ahead and solve for v naught. So v naught, actually this should have been a plus. I apologize, because we moved it over, it became plus. So v naught is going to equal, if you take the square root of both sides, this is all my abbreviations for making life a little bit simpler. Take the square root of both sides, you get plus or minus the square root of, you get, let me see, what do you get? You get 58.86 on top divided by this bracketed term, sine of a double angle minus cos of squared of that theta naught. Okay, that's all great. One thing that we need to point out before we move on is that we will reject this negative root, and the reason why we will reject that negative root is because it is meaningless to talk about a negative speed. You never say, I was traveling down the freeway at minus 70 miles per hour. That's just plain meaningless from a scalar standpoint of speed. Okay, so now the question is, as we said at the outset of the video, we're trying to find the smallest speed v sub 0 or v naught. And well, here is a very important note that I'm pretty sure if those of you who have taken some calculus, you will know exactly what I'm talking about. So to find v0 as a min, okay, what do you suppose I would have to do to make v0 be the smallest possible value? If you look at this term that we just found, you'll notice that the square root of the numerator isn't going to change. The square root of 58.86 is a constant. But if you look at the denominator, in particular, you'll see that you have this sine of a double angle minus cos squared of an angle, single angle. Well, that can change depending on the angle of theta naught. And so in order to make v naught to be the smallest possible value, you want to make this thing on the bottom the biggest value possible. So to find v naught as a min, we explore, I'm going to relabel the bottom stuff as f of theta, function of theta is sine of the double angle minus cos squared of the single angle max. We explore where f of theta is max. Okay? Well, and this is what I was referring to just a second ago. You're probably ahead of me already, because if you've done some calculus, you know that what we're really trying to do here is take the first derivative of f with respect to theta and set it to 0. And if we do that, I'm going to take the derivative of this first term. It's going to be cos of the double angle, okay, times, now I have to do the chain rule, okay, so chain rule of the argument, and so that's going to be 2, okay, so the derivative of 2 theta naught is just 2, minus, I'm going to write this other term as cos of theta naught squared. Okay, that's the same thing as cos squared of theta naught. And so we do the same idea. The 2 as the exponent comes out in front when we do the derivative, and we get cos of theta naught. We knock down the power by 1, so it was 2, now it's 2 minus 1, which is 1, times we do the chain rule again over here. And when we do the chain rule, I have to do the derivative of what's inside of this parentheses, namely, the derivative of cos theta 0 is minus sine theta 0. Okay? And like I said, and like you know, I'm sure, we have to set that to 0 to find an extremum value. So let's do this. Let's see what we get. We have 2 cos of a double angle minus a minus is a plus 2, let me write the sine of theta 0 first, cos of theta 0 is equal to 0, and lo and behold, we have what we saw before. We know that this is, okay, we know that 2 of sine theta naught cos theta naught is sine of the double angle, and so we're getting that 2 cos of the double angle plus sine of the double angle is 0. And let's go ahead and bring a term over to the other side. So I'll go ahead and just take this term to the other side. I get sine of a double angle is equal to minus 2 times cos of the double angle. And now let's go ahead and divide both sides by cos of the double angle. And if I do that, I get tangent on the left of the double angle is equal to minus 2. And this is where we expect an extremum to be occurring. And I write extremum because I'm not so sure if it's really a max or a min. But I am anticipating an extremum to occur here. So now you've also probably done this in calculus to determine, to see if max, let's do a second derivative, and I'm going to impose, so let me write this out. Take second derivative and impose that it be negative. In other words, here's the little schematic I would do. We know that if it's going to be maximum, it's not going to hold water. If it's raining, it's not going to hold water. So we expect that the curvature, or the second derivative, let me say, is going to be negative. And so let's do that. So here we go. I had already that the df d theta is 2 cos of the double angle plus sine of the double angle. Let's just take one more derivative of that. Okay, so let me write that out here real fast. df d theta we found was 2 cos of the double angle plus sine of the double angle as well, sine of 2 theta naught. Now I'm going to take a second derivative with respect to theta. And so it's really taking another derivative of what we did in the first derivative. So we get, let me go a little faster this time, we get minus 4 times sine of the double angle for this first term, this term right here, when I take its derivative with the chain rule, plus 2 times cos of the double angle. And I'm going to impose that this be negative. Okay, this is what I mean by impose that it be negative, because I want to determine the domain of where this double angle is actually going to be negative. So let me go ahead and solve for this. We can say that, alright, so we get minus 4 sine of the double angle. In fact, you know what I'm going to do? Let me just make a small substitution. This is not that important, but I'm going to let omega naught be the double angle. Okay? So, in fact, I'm going to write this as omega naught, just so I don't need to keep on saying double angle, double angle. We'll just say this is omega naught. Alright, so we get minus 4 of omega naught, and then I'll take this to the other side, so we get is less than minus 2 times cos of omega naught. Alright, and now I'm going to divide. Let me divide both sides by cos of omega naught. So then I get minus 4, look at this, tangent of omega naught is less than minus 2. And now I'm going to divide both sides by minus 4. And if I do that, look at this. I'm going to get tangent of omega naught. And before I put the equality, I'm going to write the result on the right-hand side. Minus 2 divided by minus 4 is a positive 1/2. But don't forget from your basic algebra that the orientation of that inequality changes direction. So this is the domain. So domain, let me write this way. Domain for which omega naught will be max, will cause function to be max. Let me say will cause function to be a max. Okay, and if you actually solve this on your calculator, you can see that we're and I urge you to just get your calculator out and try this. So omega naught has to be larger than arctan of 1/2, so that means that it's got to be larger than 26.565 degrees. All right. Okay, yeah, let me just stay with that for now. So omega has to be a value larger than 26.5 degrees, basically. And now let's go to a diagram that we've seen in my video on Newton's method. And here we have, basically, we have omega. I'm going to plot omega naught versus tangent of omega naught. And you get these red curves. Okay, so this is a picture that I think is familiar to anyone who's studied some trig. And notice that the tangent of omega naught it's a periodic function that goes with a period of pi, namely this amount right here, from here to here is pi radians, okay? And notice that if I were to focus on this curve right now, if I were to look at this curve, notice that you have an asymptote at the left of minus 90 degrees, and of course on the right hand side of positive 90 degrees. And the value that we just found for omega naught, we said was, oh, I didn't do that. Let me see. Yeah, the extremum, I should have done this here. So tangent of omega naught is minus 2. From here we would have found that omega naught is equal to, let me see, what is that value? It is 63.43 minus 63.43 degrees. Okay, so this is really no good. Let me point out that this is no good. And the reason why it's no good is, I'll give you two reasons. Let's go back to the original diagram. First of all, for theta to be negative, okay, I'm now talking about omega naught, but it's related to theta naught. For it to be negative would mean that we're kicking the ball into the ground. But a more compelling reason, even though that's a great one, is what we did with the second derivative when we found the domain. And we said that it had to be larger than a positive 26.5 degrees, and well, minus 63.43 degrees is definitely not larger than 26.5 positive degrees. So that's two reasons why this is no good. But let's just look at the minus 60, whatever that was, 63.43. If this is 90 degrees, the minus 63.43 degrees, let me do it in a different color altogether. Let's pick pink here, is going to be somewhere down around here. Okay, this is approximately minus 63.43 degrees. And that's no good. We already said that's no good. But we also pointed out that tangent of omega naught is periodic over pi radians. So if I just were to go over pi radians and find its partner in crime, let's see what that value is, and I suspect this is going to be good. Well, that is just adding pi radians, or 180 degrees, to the value that we had. So let's do that. So we have minus 63.43 degrees plus 180 degrees gives us a value of 116.57 degrees, which is good. This is good because it is larger than 26.5 degrees, which is what we were expecting. So this value right here seems to be a good one. And now let's go ahead and plug it in to our equation that we found way back here. Let me copy and paste it. So let me see if I can do that. Okay, here's that equation. I'm going to copy this and we'll paste it down here. Okay, and I'll just get rid of this reject the negative root. We already know that. So let's plug this value in. Okay, in fact I pasted it in the wrong spot. Let me see if I can paste it in the right spot for us. I wanted to paste it somewhere around here. Let's see. Okay. Alright, so let's go ahead and plug everything in. So we get that V naught, and I'm going to call it min now, is going to be the square root of 58.86 over sine of that angle, which is 116.57 degrees, minus cos squared of the single angle. So I'm going to take half of that value, so half of this value. So okay, if you're not following what I'm saying here, that's omega naught. That means that theta naught, which is 1/2 of omega naught, it has to be equal to half of 116.57 degrees, and that is equal to 58.28 degrees. Okay, and so plug all of this into your calculator and see what you find. You should find that V naught min comes to, when I did it, I found it's 9.76 meters per second at an angle, at an initial angle of theta naught of 58.28 degrees. Alright, so this was a pretty loaded problem. We had to rely on, of course, algebra. Then we had to rely on some trigonometry. We had to look at some stuff we've learned, some tools that we've learned in calculus. And then we had to remember from trigonometry the picture of the tangent and know how to work with that and determine where the extremum are, impose whether or not the extremum is going to give us a max, and then determine the domain for which that's going to happen. So we had a lot of stuff going on in this problem, and I acknowledge that it was pretty involved. If this did not make sense to you, please do go ahead and send me a question. I'll try my best to answer your question, but I hope that it was helpful to you. Thanks for watching, and we'll see you in a future video.